Hello children, we know again with chapter solutions. We had studied ideal solution in last lecture. Now we are going to study about non-ideal solutions. What are non-ideal solutions? We had seen those solutions which follow Raoult's law over the entire range of the concentrations are called as ideal solution. So just opposite of that, non-ideal which do not follow Raoult's law, which do not obey Raoult's law over the entire range of the concentration. They don't obey Raoult's law over the entire range of concentration. This we have seen last time. For ideal solution, that they follow Raoult's law over the entire range of concentration, and non-ideal solution do not follow Raoult's law over the entire range of concentration. That means PA is not equal to PA not XA. PB is not equal to PB not XB. That means P is not equal to PA plus PB. So if it is not equal, then what will it be? Either it will be greater than, PA will be greater than PA not XA, or smaller than PA not XA. PB will be greater than PB not XA, or it will be smaller than PB not XB. And P will be either greater than the sum of two partial pressure of two components, or it will be smaller than the sum of partial pressure of two components in the liquid solution. So it will be either greater or smaller. Thus, if it is equal, then it follows Raoult's law. If it is not equal, then it doesn't follow the Raoult's law. So we'll see when it does not follow the Raoult's law, what's the difference? As we have seen in ideal solution, they were having molecular size similar. So here they may vary in the two components may vary in molecular size, or they may vary in structures, or the force of attraction between the particles of two components are of not same order. So these three factors which affect their behavior when they are mixed. So if molecular size is same, structure is same, force of attraction between the particles of two components is same, then we'll find they follow the Raoult's law, they become ideal solution after mixing. But if they vary in these three things, molecular size may be different, or they may have different structure, or they may have the force of attraction between their particles or of different order or different range, then they are making a non-ideal solution after mixing. So we'll see the characteristics of non-ideal solution. What are the characteristics of non-ideal solution? If del H mixing is 0, then it is ideal solution. So here first characteristics will be del mixing H will not be 0. It will not be 0. That means either it will be greater than 0 or smaller than 0. That means enthalpy either increases or decreases on mixing the two components. Means total enthalpy either increases or decreases. That means it changes. Second, del mixing V is also not will be 0. That means the volume of two components separately before mixing is different and the volume after mixing is different. That means either contraction of liquid has taken place, or expansion of liquid has taken place. Either of the two conditions have been there. So volume changes after mixing the two components. Third, do not follow Raoult's law. Do not follow or obey Raoult's law. In the start only I have told you this thing, that don't follow Raoult's law. That means partial pressure of component A in the solution is not equal to the product of partial pressure of pure component and its mole fraction. Similarly, PB is not equal to PB not XB and P is not equal to PA plus PB. That means P is not equal to PA naught XA plus PB naught XB. This del mixing H enthalpy doesn't remain same, volume doesn't remain same, do not follow Raoult's law. These three characteristics. And last, about the interactions. Molecular interaction will also not be of same order before and after mixing the two components. So fourth characteristics, that molecular interactions between the particles of two components are of not same order. Either they are stronger or they are weaker after mixing. Suppose component A have the force of attraction between AA or B is having BB. We'll find AB is either more than AA and BB or lesser than AA and BB. So new forces of attraction may be larger than the earlier forces or may be weaker than the earlier forces. And because of this, we will find the solution doesn't behave ideally. It is called as non-ideal solution. So we have seen either enthalpy increases or decreases, volume increases or decreases after mixing, or we see the molecular interaction either become stronger or weaker. We have seen either the partial pressure of component A is more than the product of vapor pressure of pure component and its mole fraction, or it is lesser. So we'll see that it is showing deviation from the Raoult's law. It is not following the Raoult's law, it shows deviation. So it shows either positive deviation or negative deviation. So we'll see Raoult's law showing positive deviation and Raoult's law showing, non-ideal solution following positive deviation or non-ideal solution showing negative deviation. Now, so we'll see that non-ideal solution showing positive deviation from the Raoult's law. Positive deviation means what? Now here we will see del mixing H enthalpy is greater than 0, that is positive. It increases, enthalpy increases after mixing the two components. Del mixing V volume is more than 0, that is positive. Expansion of liquid takes place when two components are mixed, the volume increase, so expansion of liquid takes place. We see that for Raoult's law, Pa is greater than Pa naught Xa, Pb is greater than Pb not Xb. So P will be greater than Pa plus Pb. Hence P will be greater than Pa naught Xa plus Pb not Xb. So last molecular interaction AB formed, new interactions formed between the two components in the solution are weaker than the force of attraction between AA and force of attraction between BB. So we'll see interactions between solute particles and interaction between solvent particles are stronger than the new forces, molecular interaction formed between solute and solvent. So we'll see graphically positive deviation. Once again, just revising here, non-ideal solutions show either positive deviation or negative deviation. When they do not follow the Raoult's law, so they show either positive deviation or negative deviation. If they show positive deviation, that means enthalpy increases after mixing the two components, volume increases after mixing the two components, and the Raoult's law, Pa will not be equal to Pa naught Xa, it will be more than Pa naught Xa. Pb will be more than Pb naught Xb. Similarly, total pressure of the solution will be more than the sum of the partial pressures of the two components. So, and also the molecular interaction newly formed are weaker than the molecular interaction earlier existing between the solvent-solvent particles and solute-solute particles. So, they show the positive deviation. We'll find the vapor pressure of solution is greater than what is expected. So we'll see graphically now. For positive deviation, we'll see graphically. We had seen graph for Raoult's law for volatile liquids, for solution containing volatile liquids. This was the Xa equals to 1, here Xa equals to 0, here Xb equals to 0, here Xb equals to 1. Here X is plotted, here vapor pressure is plotted. So we have seen with the increase in mole fraction, there will be increase in the vapor pressure. This is Pa naught. Similarly for Pb, this is Pb naught, and this is when we join the two maxima, this curve is for P. This curve is for P, Pa plus Pb. Now this curve is for Pa equals to Pa naught Xa. This curve is for Pb, straight line for Pb, Pb naught Xb. We'll see that in positive deviation, this instead of being a straight line, the curve becomes like this. This will be the curve. That means Pa is greater than Pa naught XA. This also becomes not a straight line, rather it becomes a curve, because where partial pressure of component B is more. So we'll see it will become PB becomes greater than PB naught XB. Similarly, this total pressure of the solution also is greater than what is expected. P is greater than PA plus PB. So here the solid line shows the graph or plot or curve for ideal solution. Ideal solution. That means expected graph. But this broken line shows, dotted line shows positive deviation from Raoult's law. That means it is for non-ideal solution, not for ideal solution. So it is observed value, observed graph for the solution. Now examples for non-ideal solution showing positive deviation, that is ethyl alcohol mixed with cyclohexane, acetone and carbon disulfide, acetone mixed with carbon disulfide, acetone with ethanol, carbon tetrachloride plus chloroform, ethanol and water, See here, ethanol is alcohol, acetone is ketone. We'll see acetone is here, ketone, carbon disulfide is a different compound. We'll see that they are not having same structure or same molecular interactions or same molecular size. So they vary in all these things. So they show deviation from the ideal solution, deviation from the Raoult's law. Now we'll see non-ideal solution showing negative deviation. Non-ideal solution showing negative deviation. Just opposite of solution showing positive deviation. Now it's easy for you. Here we will see del H, del mixing H is lesser than 0. That means heat is evolved, process is exothermic. Heat is evolved, process is exothermic, enthalpy decreases. Del mixing V is lesser than 0. That means contraction of liquid take place. Before mixing, the two components have the total volume more, and after mixing, the solution will be having lesser volume. The contraction of liquid take place. This is negative. This value is also negative. We'll see do not follow Raoult's law. So doesn't follow Raoult's law, that means PA is smaller than PA naught XA, PB is smaller than PB naught XB, and total pressure of solution is smaller than PA plus PB. P is smaller than PA naught XA plus PB naught XB. So this means total vapor pressure of solution is lesser than what is expected. Last but not least, that molecular interaction newly formed between the solute and solvent, they are stronger than the interactions between the solute and solvent. That means these are stronger than the interaction AA solvent and interaction BB solute. We'll see graphically now. Just remember, opposite to non-ideal solution showing positive deviation. Now similarly, graph will also be opposite. Here vapor pressure, here also vapor pressure, X, here XA equals to 1, XA equals to 0, XB equals to 0, XB equals to 1. When XA is 0, whatever vapor pressure is, that is for pure component, that is PA naught. When XB equals to 1, XA is 0, whatever vapor pressure is there, that is due to PB, due to B component. So we'll see with the increase in vapor pressure, there will be increase in the So this is as per Raoult's law. If they are ideal solutions, this should be the curve for PA, this should be the curve for PB, and this should be the for P. Now we see that they are showing the negative deviation. That means PA naught XA is smaller than what is expected. So the curve will be like this. This will be the PA, which is equals to PA naught XA. This will be the curve PB, which is smaller than PB naught XB. And this will be the curve for the solution, that is P is smaller than PA plus PB. So solid lines show for ideal solution which follow Raoult's law, that is expected value. This is observed value, which is for the non-ideal solution showing negative deviation from Raoult's law. That means these are observed values. Examples, if we see, we'll see that alcohol and acetone and chloroform, chloroform and diethyl ether, chloroform and HNO3, water and HNO3, and many more examples are there. So we had seen what are non-ideal solution, how they show positive and negative deviation. We'll be studying for azeotrope in our next class.